Okay, so Ulrike, thank you for taking your time to present for our webinar. And without further ado, um, please go ahead when you're ready.
Okay, well, thank you, first of all, for the invitation. I really appreciate it. And I will talk about xSDK. And I just realized I forgot a T here. So anyway, so you know. So the xSDK actually stands for Extreme Scale Scientific Software Development Kit. And it is an ecosystem. So as I get started here, I do want to talk about what an ecosystem is. Can everybody hear me well? Just want to make sure.
Sounds good.
Yes.
Great, thank you. Okay, so what is an ecosystem? So according to the definition here, a group of independent but interrelated elements comprising a unified whole. So in our case, the elements, of course, are the math libraries, and the xSDK is the unified whole. So what's the thing about ecosystem is they're very challenging. And one of the reasons they're challenging is because you do have these independent elements that are somehow interacting, but you want to have them together. And the really hard part is, how do you make them all play nice together? How are you able to get a very effective ecosystem together? And so this is what this is about, this talk, essentially. What are we doing to make sure that the xSDK is such an effective ecosystem? One of the nice things about if you actually can create an effective ecosystem is that the impact of the total ecosystem actually is more than the sum of the impact of the individual elements. In other words, you might have some wonderful, great libraries by themselves, but if an application uses several of them together and they don't play nicely together, then the impact of the individual elements doesn't mean anything. So, okay, so here's just xSDK. Why did we actually even look into this? And you can consider we want the xSDK to be part of a bigger ecosystem, actually, which includes large-scale science applications. And of course, the focus at that time was extreme scale. We want to be able to go to exascale. And that's where you have a variety of applications. They will need to use a variety of different math libraries. And you want to make sure that they're able to build everything together easily, efficiently, etc. And any of you have ever built a big application code that uses a lot of different libraries knows that this can be a really big pain for a variety of reasons. So here I give you a brief outline of my talk. I will give you first a brief history of the xSDK. We'll briefly talk about the different elements of this particular ecosystem, and then talk about how do we actually achieve an efficient ecosystem. So let's get back to the history. So the xSDK, the whole work on it actually started in 2014. So that's 9 years ago. And at that time, there was a collaboration between two offices of the Department of Energy, the Office of ASCAR, Applied Scientific Computing Research, and BER, Biological and Environmental Research. And one thing BER wanted to do, they wanted to create a really big, large, multi-scale, multiphysics subsurface hydrology model. And in order to do these kind of simulations, they required a variety of different software packages. So here in light blue, you can actually see the application codes that were involved. And in orange are some domain components, which give you some physical parameter things, physical things that are being computed. And then finally, you do have the math libraries. In this case, there were actually only 4 math libraries, but even here you see they do have some interoperability together. And even at that time, even so there are not that many products involved, there were already issues trying to build this together. And you could have namespace conflicts. Some of these libraries might have dependent packages underneath where they're used by the same libraries and might use different versions or things like that. All of these can cause issues when you try to build them together. So at that time, the IDEAS project was created, which was really a first of a kind project in that the focus here really was on productivity and sustainability of software. Generally, the Office of Science would more look into science cases, algorithms development, etc. But this one really focused more on sustainability. And this was originally led by Mike Haru, Louis Kirkman McInnes, and David Moulton. And there were basically 3 areas that they were looking at. One was the use cases, of course, to generate this model that BER wanted. But then they also were considering methodologies for software productivity, trying to understand those and make sure we can get overall better software knowledge that can be given to others as well. And then, of course, we developed the extreme scale scientific software development kit, the xSDK. So that project ended in 2017. So it was only a 3-year project. However, before it ended, it was continued actually in the exascale computing project. And I'll say a little bit more about the exascale computing, or ECP, in a little bit. Under the ECP, the xSDK ECP project was started that focused on the xSDK in particular, but I mean the other parts like the software product, etc., were also considered. There's still another ideas project under ECP. And so the xSDK then became sort of the key delivery mechanism for these ECP math libraries to make sure they were working well for the application codes in the ECP. And of course, there was a lot of work for the individual math libraries to make sure to port them to the new machines, but there was also a lot of work on the xSDK ECP team to make sure that they were working well together. So here I just want to say a few things about the exascale computing project that sadly ends at the end of this year. And that actually consisted of 3 different parts, which all came together in a very great way with a common goal. So there were the applications, codes on the one side, there are many of them. Then there was a software technology, which have a variety of different types of software technologies, not just math libraries, but also programming models, development tools, data and viz tools, etc. And there, the software, scalable software stack is actually E4S. And then, of course, there were the actual hardware, the machines that were being built. And what's really great about this project was this great collaboration that was happening, because everybody was trying to help everybody else to make sure we were able to achieve the goal of achieving exascale computing. And of course, for us here, we just look at the math libraries for this talk. Here, just for the fun of it, was the roadmap of DOE to the exascale systems, which I updated a bit because it's shifted a bit. But you see, we do have Frontier available. Aurora is being set up as we're speaking. My understanding is all the parts are there, and they're just working on putting them together. And then, of course, El Capitan will hopefully will be actually put together next year. That was originally planned for this year, but it skipped a bit. And so these 3 exascale machines here, all of them use different kinds of GPUs, and that's also the case for Perlmutter. So all of these use GPUs. And for a lot of the math libraries at that time, in 2016, they did not have the ability to run on these machines and use their capabilities. Or I should say, at least use their GPU capabilities. So the other part that was really important is we do have a variety of different application teams working on all kinds of applications here. And I put them here because just as examples that many of them used a variety of different math libraries in combination. And you can see here, some of them use 6, 7, some of them might even use more, maybe some of them not quite as many. So you can see that here. And so that was another reason why it was really important for us to make sure that the xSDK would work well for them. So our very first xSDK release came out in April 2016. At that time, we only had the 4 libraries, which were the original hydrology model that were needed there. And you can see they had these interoperabilities between them, some of them kind of tricky, like PETSI, Trilinus, have each calling each other. And there was one domain component at that time, and the installer at that time was a PETSI-based xSDK installer. So fast forward, what we have, our last release was last year, but we're actually working on the final release for ECP, which will be version 1.0.0. We decided to finally move over to 1. I think we are mature enough to do that. And at this point, you can see we have a lot more libraries, so many, as a matter of fact, that we had to leave out the interoperabilities here, but I will show you a graph which tells you how complex this whole thing is. So at this point, we have 2 domain components, 26 math libraries. And actually, starting since the second release, we started to use SPAC as our package installer. So, yeah. So let me move on to talk about the elements of the xSDK. So there are basically three of them. Let's start with the SPAC, the package manager. So SPAC is actually flexible package manager for high performance computing. It's open source, so you can download it here. It's used by many applications, etc. And it's become really, really crucial to allow you to build fast and efficiently. So here is the current dependency graph for the xSDK 0.8.0 that was generated by SPAC. And so the green dots are all the xSDK math libraries. The gray ones are libraries that they depend on. So you see how really complex the whole xSDK build is. It involves a lot more than just the individual xSDK libraries. And so it's really good that we are able to use SPAC to build them. And the nice thing about SPAC is that for a variety of different platforms, you can build the xSDK by just saying SPAC build xSDK. In some cases, you need to do more. So the individual math libraries, there are 26 of them right now. Here you can see, and just for the fun of it, I wanted to put down the different logos to show you how different they are, how diverse they are. So each of these libraries is truly independent from the other in a way that they're independently developed. And they have all their own software strategies and their own flavors of how they want to build and develop their software. And so you can imagine if you have all these different people coming together, that could cause conflict when you're trying to make them work together. Kind of like imagine you have a painting and you give different portions of the painting to different groups and you just say, go ahead and make your painting. If they don't communicate with each other and you just put it together, you generally would get a pretty awful painting. And that would be the case with the xSDK. So in order to make sure that they're all placed nicely together, we had to do something. And so we started to come up with a variety of different guidelines that help to address certain challenges we had to deal with to make sure these libraries are interoperable and that they work well together. And those are the xSDK community policies, which you can get a paper version over here. And we also have it on GitHub where you can even go in there and make pull requests, comments, etc. We definitely like to have feedback for those. So the current version of the xSDK community policy, which is actually 1.0.0, has 17 mandatory policies, which satisfy a lot of variety of different issues like how to configure, how to install, testing, portability. All of the libraries have to be open source, hopefully a permissible license to make it easier for people to use them, etc. And we do also have a bunch of recommended policies, currently 8, and they include error handling for how to free system sources and things like that. So in order to become an xSDK member package, the package has to be compatible with the 17 mandatory policies, and of course should try to do an effort to also fulfill the recommended policies. And on top of it, it should be used use another package in the xSDK, meaning there's an interoperability between them. And then of course the interface should be regularly tested for regressions by the calling library. And so this community policies really helped to create a lot of positive effect, making the xSDK very effective. And again, like I said before, if you want to take a look at them, we encourage feedback and contributions for this. So here are the current policies, the short versions. I'm not going to go to them, so don't be afraid. In red are just the ones as we do occasionally or regularly update those. And so these are the new ones. These two is now they're required to have a publicly available repository and to provide sufficient documentation were actually originally under the recommended. We ended up moving them over. And then we have a couple new recommended ones. I mentioned before, regular review these policies because software practices change. And so we want to make sure we're always up to date. And so we do seek community input for that. We discuss the feedback, and then there is a consensus vote among the packages because we do not want to accidentally kick people out or whatever. We do want to make sure that we all have a good understanding and we agree on these things. For packages that want to join, we actually have a form that they can fill out to see how far they're compatible with their routines. And again, and this is also available on our xSDK project on GitHub. So, and that it also provides examples of all the current ones, how they filled out the forms, so people can get an idea. So you can put on the support of these, and then there are always some notes, which can be helpful to other packages who want to join. So what is really required to get an effective ecosystem? I mean, here are the phone quality we really want to have. We do want to have a high software quality, portability, interoperability, and then we want to be able to sustain this, of course. So the community policies are really very important to enforce a lot of these qualities. For example, for software quality, we have a variety of different policies that really make sure that we get good software quality. For example, M2 is to provide a comprehensive test suite. So all of our xSDK libraries do a lot of testing, CI testing, and making sure that as they're growing and changing, that they continue to be of good quality, they continue to work, etc. And if they do testing, they also want to make sure that they test memory corruption issues, etc. And make sure that they don't bring old bugs back in, etc. So that's why it is really important to do this regular testing. Other things they do, they're trying to use a limited and well-defined symbol macro library and include file namespace. It's important to use something unique. You don't want to use any common namespaces to avoid clashes. And then, of course, it's really important to provide documentation for the users so they're able to use the library and know how to use them. And also for further development. Since many of our libraries, I mean, all our libraries are open source and they're out in the public, many of them allow users to also contribute to the libraries. And so it is good to provide some rules for further development to make sure that your library is somehow consistent as it grows. Another thing is really portability. And so we do have a mandatory policy which says, give best effort at portability to key architectures. So since we are working towards exascale, I mean, what are the kind of key architectures we are concerned about? Of course, it is the high performance computers. And so all our libraries are really working towards that. And of course, we also make sure that the libraries work on general, like Linux boxes, laptops, etc. They usually do. We also test those as we're making new releases. But for exascale, of course, our target is always the exascale machines, right? I mentioned that before we were looking at them. All of them had these GPU architectures, different ones. It started with NVIDIA, AMD, and Intel. And so at the beginning, many of the libraries, some of them might have had CUDA support, but then HIP and SYCL, which is what you use for AMD and Intel GPUs, weren't really even around at that time. So it was really important for all our libraries to also work hard to make an effort towards those. And so how did our libraries actually achieve that? So many of them actually use portable programming models that provide abstractions. So one of them is Cocos, which is developed by Sandia National Lab. And so that allows you, just gives you abstractions for your loop. And Raja is a similar one that's developed at Lawrence Livermore Lab. And it then is up to these teams, Cocos and Raja, to make sure that if you use these programming models, these abstractions, that they connect you to these different architectures. Some other ones are SYCL and HIP that claim that they will also be able to be portable. SYCL is developed by Intel and HIP was by AMD. So we'll see how that goes. Another thing our libraries have done is trying to limit the code that interacts with the devices. Like Steve Jobs says, the way you get programmer productivity is by eliminating lines of code you have to write. And of course, if you only have a limited amount of code that needs to be changed when you port, you can do this much faster. And so a lot of them try to do this, that they can define things at one place in their code. And so they don't have to go through the whole code when there's a new programming model, a new machine comes along. Then, of course, the vendors do provide fast kernel libraries. For example, there's cuBLAS, cuSparse from NVIDIA, RockBLAS, RockSparse from AMD, and then MKL from Intel. And so you would assume that the vendors will make sure that their fast kernel libraries specifically designed for the architectures will perform well. And so it's good for the libraries, the math libraries, to take advantage of that. Then many of them, because we started with NVIDIA and GPUs, had started to write their own CUDA kernels. And so vendors have provided tools to port these kernels to the different HIP or SYCL, to the different programming models. And so many of us try to do that as well, to use these tools, for example, for HIP, HIPify your CUDA code. HIP and CUDA are quite similar, so that works fairly well. Intel also has a tool to help you to go to SYCL. SYCL is a little different from the other two programming models. And then, of course, if you have really an algorithm that's totally unsuitable for GPUs like structure, they like to have large problems, etc., then you might actually have to sit down and develop a new algorithms. For a mathematician, that's probably the most fun part. It's the most challenging, but it might give you actually the best results. And in some cases, we actually have done that. For example, hyper-developed some new interpolation operations. And the nice thing, if you do this, and they might end up giving you better performance even on CPUs. So, okay. All right, interoperability. Interoperability is a very large topic for the xSDK, because you know that, and I'll talk some more about it, it is actually a condition to become a member. And so we do have a variety of policies to make sure that these packages work well with each other, like respect system sources and settings made by other previous called packages, allow installing, building, and linking against an outside copy of the external software. So you don't want to have internal versions of software inside and things like that. And then there are a variety of different other ones under the recommended area. And so interoperability is really challenging, and you can look at it in that there are different types of interoperability, different levels. So you can already consider interoperability if you just use the packages side by side in an application. Even just building them together can be a challenge, because you saw originally the spec dependency graph, how complicated that can be underneath those packages even. Then level 2, you would exchange data with each other, and it becomes more challenging. And finally, level 3, which is really the interoperability many of xSDK libraries have, is that one library calls the other one for unique computations that are needed within the calling library. And here are some examples. For example, you might have a multiphysics application, and which has these two different applications underneath. Application A might want to do some time integration, has some problem, a time-dependent problem, uses time integration from Sundial. And then Sundial wants to solve a linear system, might call PETSI underneath, and that system wants to have a very scalable preconditioner called Hyper, IMG from Hyper, for example. So you have these three libraries working together. Application B now might want to use a finite element discretization for their problem, uses DL2, for example. D2 might call Trilinus for their linear solver, and that linear solver needs something more sophisticated underneath, because the iterative one doesn't work that well, and then connects to SuperLU as a direct solver. So you can see you have all these different libraries here have to work together when application C calls. So I showed you earlier the dependency graph. Actually, those dependencies you saw were only the blue ones. There are a lot more interoperabilities between different packages, all the 26, because when we actually build the xSDK, we have to disable some, because otherwise the whole package won't build. But that's okay. These other interoperabilities are still used, because application codes generally don't use all 26 libraries. They use a subset, and then they can build it with their spec package in the way that all these other interoperabilities also work. However, what we really want, of course, in the long run, we want to make sure that these yellow points turn blue. So one thing we also did in order to demonstrate interoperability, we actually built a sample code suite that's available on GitHub, where you can go and you can have some example codes that show you interoperability between different packages. What you have here, currently there are about 20 of the xSDK libraries represented, and these are the interoperabilities. The different colors just means that these were the ones we added in our most recent release, which I think was 0.4.0. You can build them with spec install xSDK examples, but not all of them can build it this way because some of them are new ones that were not included in the last xSDK. So we also provide a simple build via CMake, and there's also C-test included. And so it actually turned out that this test suite ended up becoming an important piece for our xSDK testing strategy plan. And I mentioned sustainability. Yes, we do have sustainability policy also. But let's get back to the overall release when we actually built the xSDK, when we have regular release, which we are working on right now. You can actually see here, we do a lot of different testing. So in every time we have been extending the number of libraries, you can see here over the years what has been added. So gradually the xSDK has grown. And then we have done a lot of environment tests, and this was what we did for the last release last year. We actually tested on Summit, Crusher, Polaris, Perlmutter, also besides the general variety of different Linux boxes, Apple laptops, things like that. We did all these, right? And so we also have special option for ROCm, like for AMD GPUs and CUDA for NVIDIA GPUs. And if you want to have specific instructions how to install, we have them here. Sometimes we can't just use the simple spec install xSDK. We have to add something else, or we make some changes, and we do provide instructions for that also. Of course, for the current ones, we're actually also testing on Frontier. So, okay. There we do have a 2-level release process. The basic thing I just want to say, if you want to get the latest release, you can get that here. Don't want to get too much into this right now. But I do want to say something about the challenges we actually face. One of the things you have to consider, we release xSDK once a year, but the individual libraries as well as spec continually has releases in between. And so that makes it very difficult for the xSDK to stay current. And that causes us a lot of problems. So every time when we actually start a new release, we have to consider what has changed, what is still working, what's not working. So also when we test the xSDK, what happens is generally if you build the whole package, one package breaks, and it's a sequential process. So we go in there, we try to understand what's broken, we fix it, and then the next package breaks. And so that can take a while. And so that was one thing we had to deal with. It's this. We also have to have a lot of people to take care of this. And so in order to improve this whole testing process, we actually designed a test plan. And so that's where we realized including the xSDK examples test suite is a really good thing to not only build, but also test if our codes run afterwards, because we can then just run the individual example codes, right? And we also thought about, in order to break up the sequential process of one code breaks and then the next one breaks, etc., we actually defined hierarchical test layers to improve our testing process. And so what do we actually mean by hierarchical test layers? So first of all, of course, you saw from the community policies, each xSDK library has to do their own testing. That's our first level. Second level, they have to test the interfaces between libraries. Again, a calling library has to test the interface to the library they're calling. Again, that's something up to the individual libraries. But then we decided it would be good to also start including subsets of there. And so that's where you end up with some subsets of interoperable packages. And not only did we make them subsets, but we also included development packages to find issues like API problems, etc., early. And then the final level would, of course, be test the whole xSDK. And so we do have the current test setup here. This was what's done for 0.8.0. We do have some pipelines. We test on a variety of different platforms and so on. We test the xSDK. We exclude the xSDK examples. We test CUDA. We also test other things to be able to catch this. So these are a variety of subsets we actually included with development versions here. You can see how we have different of these packages bunched together here, like whatever, PETSI, SLAPSI, POOF, Rotan, Hyper, Super, dist, or down here, we have some more MFEM, Super, Strumpec, PETSI, SLAPSI, PUMI, Sundials, Hyper, etc. We run it both for CUDA and others. And so that really helps us to make sure testing goes on and catch testing earlier, and breaks also up the sequentiality of testing I mentioned before. The other nice thing about this is actually allowed us to update our interoperability matrix. So some of the yellow dots now turned magenta. And that means that our interoperabilities we now can test because we have these xSDK examples and we have the subset jobs. So, you know, okay. Okay, and that brings me to the end. Obviously, we do have future plans. We would like to continue updating community policies. We and about to release a new xSDK release. And we would like to improve all of these things. We don't really know how that's going to happen because ECP handles is ending. And so we don't really know. But again, if you want to learn more about our project, you can actually get this on our website, xsdk.info. We always update this when we have a new release, I guess it will be updated within the next few months. And you can also get our community policy there. And of course, all this required a whole huge amount of work, and the xSDK CP project is really huge. So I mentioned a lot of people here, not all of them. Yes, it does take all kinds to make a great ecosystem. And you can see also there were a lot of different institutions involved in this project. So thank you very much. Okay, somebody raised their hand. Should I just take questions now? Oh, Rio, are you going to do that?
Are you going to continue moderating?
Okay, I mean,
I think going on to questions is a great idea, Ulrike. So thank you so much for speaking. This was a really informative presentation. We appreciate
thank you
sharing your insights.
So let me see where somebody raised their hand, but I don't actually know how to do this. So, and that hand disappeared. So, oh no, up here, Kapil, right?
Yeah. Hey, Ulrike, yeah, that was really nice, informative. I have two quick questions. One was specifically that, Petsy and Trillinos are two parallel solvers, and somewhere you talked about they don't always talk to each other much, or the integration is an issue. So how far have you got those? I mean, can you shed some more light on that? Does Trillinos call Petsy in the middle, or Petsy calls Trillinos, or that link is still not fully working, or how's it?
I'm assuming it's working. So I assume that Petsy can call Trillinos solvers and Trillinos can call Petsy solvers. But of course, this was a very tricky effort. And I think Lois probably knows more about this because she knows what happened in Petsy. So I do remember it was a very tricky effort to make all this work. I don't know who's actually using this right now. So that's I'm not sure. Probably Lois might know more. Do you know actually, Lois? Who is actually who's calling Trillinos from? I know there were some Trillinos packages which were called, right, through Petsy, like ML or things like that.
Yes, there's specific elements of the interfaces that are driven by the needs in the application community. And and so, depending upon those needs, those specific interfaces have been developed and are regularly tested. There's certainly not an interface for every functionality of every package, but selected functionalities as driven by the application community needs.
Right. Okay. Thank you. So, will the slides be available to us, or it's confidential information in there, or something? I don't know.
It's all reviewed and released. So they will be available. I assume. I don't know how you guys do that. I know this was recorded, so the presentation is certainly available. I don't know if you post the slide somewhere too.
Yes, Hatem Altayef, who's our website guru, will be posting both the PDF of the slides as well as linking to the YouTube recording.
Okay. Thank you so much.
Ulrike, I had actually a question. Just out of curiosity, how much Julia is available within the xSDK? Are you guys looking at some of the development being made within Julia? Are you considering it as maybe a new programming model, for math libraries? Does it work well with portability, with performance, productivity? Did you discuss this among among your partners and people?
Well, at this point, we haven't considered Julia. I mean, I agree that Julia seems to be very promising. I know we even at some point we were wondering, should we add another, somebody said, should we have a Python interface for Hyper, for example, since Hyper is a library I'm personally involved in. And we were like, well, Julia would be more interesting. But in the context of the xSDK, we have not discussed Julia. As you know, the ECP is ending, and at this point, it's unclear how the xSDK will be going forward. So I don't know if that's something. It could be an interesting topic. So maybe that's something to pick up for a suggestion to get some funding. I don't know. We'll see.
Thank you.
We welcome questions. If anyone else has a question, please raise your hand.
I have one. We're promoting HPC for all within SciAGSC. How much of the work done in the US in the context of ECP can actually be used, to help, other maybe countries also to develop some similar activities? And I've seen many GitHub link, right, open source, from the outcome of ECP available. But can you maybe give your perspective on this and maybe help some of the attendees right now who may look at how ECP has been working in the US and maybe promote the similar activities within their own country?
So first of all, of course, if you're interested in learning how to make these things work together, that's all online, and you can look for it, like the various links I've suggested. Now, if you're actually talking about how the ECP came together, that's, of course, such an effort does require a lot of funding. So that's one thing, right? So you'd have to find some kind of funding source first, and then try to find a way to make sure that all these people work well together. I think that was one of the reasons why the ECP was so successful. And we're not totally finished, but I know it was totally successful, was because we were all able to work together. So instead of people trying to hide their things, I mean, people were open about what they were learning. They were helping each other. I mean, there was this whole spirit of collaboration going on. And I think that was really extremely important to make this all work. And so generating such an environment is difficult, I think. And so, again, it does need money. It does need people who are capable of making this work. So it turned out that the whole structure actually, even so, there were times when I was not happy about the work we had to do, the milestones we had to do, but ultimately it was really helpful to get all this work done, because it was a lot of work and required a lot of people to work well and to work together. So I don't know if get funding, get people who have a similar mind trying to generate this kind of working a collaboration, right? And that would be required. It's hard to do, but yeah, if you can do that, then great things can happen.
Sounds good. Thank you.
Thanks for your answers, Ulrike. Thanks very much for the presentation again, and thanks to all the attendees for joining us today. And we look forward to seeing you next time in an upcoming Supercomputing Spotlights.